Hi students, good morning. Welcome to our physics classes. Yesterday we were discussing about the problems from center of mass, and we have defined what is center of mass, and we have calculated velocity of center of mass, position of center of mass, and while we were talking about the center of mass, we mentioned the term rigid body, center of mass of a rigid body. So to find out the center of mass of a rigid body, we use the equation related to integration. That I think you are remembering that. Anyhow, what is a rigid body? What is a rigid body? And what is the speciality with rigid bodies? That is a special topic to discuss. And what is a rigid body, and how that rigid body can react to a force. When you are applying a force to a rigid body, how it can react to that rigid body, that applied force. All these matters are focus of discussion. So in this new chapter, we are going to talk about this kind of topic. That means we are going to start the discussion on a rigid body and its properties. So you can start with defining a rigid body. And we have seen a system of particles, a system which consists of different particles. And suppose you are applying a force on a system of particles. And if you are applying force on a system, the relative distance between the particles within that system is not changing, then you can say that that is a rigid body. Obviously, rigid body is a system of particles. And the particles consisting in that system are placed at different points. And there is a intermolecular or interparticle distance at say, suppose they are having a fixed distance between the particles. And if you are applying a force on such a system and there is no difference between or difference in the distance between these particles, then you can say that that is a rigid body. Which implies if there is no change in distance between the particles, there is no shape change when you are applying a force on a rigid body. So such a system, which means the distance between the particles retained even you are applying a force, it's not changing even you are applying a force. Such a system is known as a rigid body. Such a system is known as a rigid body. So rigid body is a system of particles. When you are applying a force on such a system, the distance between the particles will not change. Such a system is the rigid body. So when you are applying a force on a body, rigid body, if you are applying a force on a rigid body, there is a chance of two kinds of motion. There is a chance of two kinds of motion. One is obviously translatory motion. It can move that particle from, not a particle, it can move that body from one region to another, system from one region to another, one place to another. That is a translatory motion. Otherwise, sometimes it can rotate about an axis. It can rotate about an axis. So, here, translatory motion we have already discussed, linear motion we have already discussed, many aspects of linear motion we have already discussed. So, as I already told you, the aspects of linear motion we have already discussed many times. But our focus is on rotational motion, or our point of view is on rotational motion. Okay, so what do you mean by rotation? Rotational motion is a circular motion. Rotational motion is also a circular motion. If a body has a axis and it rotates about an axis, I mean it moves about an axis in the circular path, then we can say that it is a rotational motion. It is a rotational motion. So remember, while a body is rotating, axis of rotation is passing through that body itself. If a body rotates, the axis of rotation passes through the body itself. So what is the reason for rotation, or what makes a system rotate? What makes a system rotate? For linear motion, we know a force is responsible for linear motion. That means if you are applying force on a body, then only that body will move. That movement is a linear motion. It's displacing from one point to another. But here, the body or the system is not displacing from one point to another, but according to a fixed point, it is rotating. It is rotating. So when you can say that in linear motion, when a body is displaced from one point to another, its position changes. In rotation, its position is not changing, but the angle made by the position vector of each particle in that system changes. The angle made by each particle, position vector of each particle in that system about the fixed point, that is the axis, is changing with respect to any of the axes. Then only we can say that that object is rotating. That object is rotating. So here, when I say an object, a particle, a body, a system, remember that is a rigid body. That is a rigid body. A rigid body means it consists of too many particles. We don't know how many particles are there, but many particle system. But the average distance between each particle will not change even though you are applying a force. That means they can translate, they can rotate, but without any change in its shape. That is a rigid body. A rigid body is a one which is not changing the distance between the individual particles inside that system even though you are applying a force. Okay, so for displacement you need a force. Here instead of displacement you can say that angle is changing, so you can call that as angular displacement. You can call that as angular displacement. And angular displacement you can denote as theta. Angular displacement is denoted as theta, which is very similar to displacement in this is linear motion and this is rotational motion. You keep these two terms there, linear motion and rotational motion. In rotational motion you are having displacement, in linear motion you are having displacement, and in rotational motion it is changed into angular displacement theta. So for making the displacement in linear motion you need a force. You need a force. But with a force, is it possible to rotate a body? For a force, is it possible to rotate a body? That is the question. The answer is no. With a force, rotation is not possible. Listen to my words carefully. With a force, rotation is not possible. But without a force, rotation is not possible. Are you feeling strange? With a force, rotation is not possible, but without a force, rotation is not possible. You're thinking that this man is crack. No. Believe me. With a force only, rotation cannot be possible. But without a force also, rotation cannot be possible. As a mere force, that force can't rotate a body. But reason for rotation is derived from force. Reason for rotation is derived from force. And that quantity or that entity or that physical entity or physical quantity or physical quantity which is responsible for rotation of a system is known as torque. That is known as torque. Torque is not a force. Torque is not a force. But it is derived from a force. That I told you, with a force, rotation is not possible. But without a force, rotation is not possible. So, suppose you are having an road here, a road which is fixed at this point, O. You are applying a force here. Suppose you are applying a force in this particular direction. This is the direction of force. What will happen to this road? Suppose it is fixed here and it is capable of moving around this object O. Okay. Suppose your door, better example is your door. It is one end is fixed and the other end is open, and it can rotate about this fixed point. Is it? Yes. So when you are applying a force at the edge of the door, what will happen? This force will not translate this door from one point to another. Then what is the need of keeping a door at the door there? So this force is not displacing the door, but it is rotating the door. The direction of the door is changing as you apply a force at the edge of a door, open door. Is it? So what makes this force is responsible for the rotation? We can say that force is responsible for the rotation, but that force is not rotating that object. We can say that the object is rotating as a result of the torque derived from this force. So we can say that the torque is defined as or measured as the force into the perpendicular distance from the axis of rotation. From the axis of rotation to the line of action of that force. So this is the line of action of this force. Is it? So from the axis of rotation, you are making a normal to this axis of rotation. Line of action of this force. So this is, suppose this angle is this is angle theta. So this is the perpendicular distance and this is the hypotenuse. So suppose this is L, the length is L. So this distance you will get as, suppose this is point A. Sin theta is equal to OA divided by L. Sin theta is equal to OA divided by L. So OA is equal to L sin theta. OA is equal to L sin theta. Therefore, what is this OA? OA is the perpendicular distance from the axis of rotation to the line of action of the force. So torque is defined as torque is equal to F into L into sin theta. That is L into F into sin theta. Okay. So suppose since you are taking it is R cross F, it is rotating in the opposite direction. So this is acting in the anti-clockwise direction. So you have to take F cross L. So when you are taking L F sin theta, the movement will be in the clockwise direction. So that will become L cross F. Torque is getting as torque is getting as L cross F. You will ask whether you can take LF sin theta is L cross F or F cross L. Both are possible, but you know this L cross F is a vector, and in which direction that vector is acting, that is depending upon the movement of this object. If it is moving in the, suppose two vectors are there, this is R and this is F. So you are taking R cross F. This is anti-clockwise. So in which direction the force is acting? According to right hand screw rule, if you are keeping the right hand screw and it is anti-clockwise direction, if you are rotating, it is moving away from the board. If you are keeping it and rotating in the clockwise direction, so what will happen? It is piercing into the plane of the board. So that depends upon the direction in which the movement happens. Okay, anyhow, you can say that torque is defined as force into the perpendicular distance from the axis of rotation. Force into perpendicular distance of the axis of rotation. So that is given by L cross F. Or in terms of general case, suppose instead of L, you are keeping a particle at P at a distance R. Then instead of L, you can keep here as R cross F, which is equal to R F sin theta. R F sin theta. So the torque is denoted by a letter tau. Ta, tau. This tau is a symbol which is equal to R cross F. Tau is equal to R cross F. This is the torque generated from a force. So we can say that if you are applying a force F on a point which is at a distance R from the axis of rotation, then the torque derived will be R cross F. Simple way. Torque derived will be R cross F, where R is the distance from the axis of rotation to the point where the force is applied, or with the rotating body. Then force is the applied force. Simply we can say that it is the distance between, or the product of force and the distance from the axis of rotation to the rotating body. That is R cross F. R cross F. So if you are taking the perpendicular distance, then it comes R F sin theta. It is the perpendicular distance, product of force into perpendicular distance from the axis of rotation to the line of action of that body. Okay, so that is the torque generated. So this torque is responsible for rotation of a body. Torque is responsible for the rotation of a body. So in rotational motion, instead of force, we can add to the torque acting. So when a force is applying on an object, it is linearly displaced. When a torque is acting on an object, it is rotated. Okay. So whenever you are having a force, according to Newton's second law, force is related to momentum. What is that momentum? That momentum is here. Momentum is P. Is a vector quantity P. How you can get it? Momentum is derived as V is equal to, or defined as P is equal to mass into velocity of center of mass. That we have already seen, or in the rigid body, we can say that it is the velocity of center of mass. P is equal to mass into center of mass. This M also you can replace by M into VCM. Okay. For a rigid body. Corresponding rotational motion, this is rate of change of dP by dt equal to F. dP by dt is equal to F. Instead of F, here you have tau. And tau is equal to r cross f. By analogy, it can be r cross or d by dt of r cross b. d by dt of r cross b, where r cross b is known as angular momentum. R cross P is known as angular momentum. See, this is P. Momentum in linear motion. How you can convert it into angular motion when you are taking R cross P? That is, if you are multiplying any physical quantity with the perpendicular distance from the axis of rotation, then it is automatically converted into its rotational aspect. It is rotational aspect, and that is known as moment. So moment is multiplication with the distance. So we can say that since r cross f or r sin theta into f, this is 2. Moment of force is torque. Perpendicular distance r sin theta is the perpendicular distance multiplied by force is torque. Similarly, r sin theta into p is equal to angular momentum. R cross p is equal to angular momentum, and angular momentum is denoted by J. Angular momentum is denoted by J. So J is equal to R cross P. J is equal to R cross P. So P can be replaced by J. Momentum you can replace by angular momentum. Slowly we can come to the conclusion that if you are taking the moment of any physical quantity in linear motion, you will get the rotational analogy. That is a comparison between rotational motion and linear motion. So moment of force is torque, moment of momentum is angular momentum. Moment of momentum is angular momentum. See, whether it is a torque or torque is r cross f. How you can evaluate that? You can make use the determinant I, J, K. R is x, y, z, and f is fx, fy, fz. Is there any doubt? Because R is equal to xi plus yj plus zk, and f has its component fxi plus fyj plus fzk. So you can easily find out R cross f in terms of the components I, J, K, x, y, z, fx, fy, fz. Okay, then what is J? J is equal to R cross P, is it? Then I, J, K, again x, y, z, then Px, Py, Pz. Okay, so these are the expressions for torque and angular momentum. Torque and angular momentum in terms of its components. Suppose you have a rigid body. And in this rigid body, this is the axis of rotation. Origin is the axis of rotation. And at a distance r, you are having a particle P. And it is getting rotated in the anti-clockwise direction. It is getting rotated by anti-clockwise direction. And it makes an angle theta at any moment. It is anti-clockwise rotation. It is having at any instant it makes an angle theta. So the linear distance traveled during that time is s, displacement. So we can say that r by radius is equal to theta. arc by radius. So S by R is equal to theta, or S is equal to R theta. S is equal to R theta. When you are differentiating this, ds by dt is equal to R into d theta by dt. Why R is not differentiating? The R is constant because R is the distance from the axis of rotation to that fixed point. So R will not change since it is a rigid body. So what is ds by dt? Linear velocity v, which is equal to R into what is d theta by dt? Angular velocity omega. So one more time we can have here velocity in linear motion and angular velocity in rotational motion. Angular velocity in rotational motion. Okay, then you are differentiating this equation. So you will get dv by dt is equal to R into d omega by dt. What is dv by dt? dv by dt is acceleration A, which is R into alpha. What is alpha? Angular acceleration. Angular acceleration. So A in linear motion, alpha in angular motion. A in linear motion and alpha in angular motion. Okay, so we for almost all the terms in linear motion we are having the rotational aspect. So again you can have theta 0 the initial position, S0 is the initial position, here you have theta 0. SF or SI, here is theta f, theta I. Is it? Then U is the initial velocity, so omega 0 is the initial velocity, V is the final velocity, and omega is the final velocity V. Okay, similarly we can have every aspect in linear motion, you can have the rotational analogy. By logic you can easily find out the relation between the linear motion and the rotational motion. As I already told you, to get any physical quantity in rotational motion, you just take the moment of that physical quantity in linear motion. If you found the rotational equivalent of displacement, you just multiply by r theta is equal to s, and f is equal to tau, p is equal to j, v is equal to omega, a is equal to alpha, like that only. Okay, so moment of any physical quantity, that is rotational aspect. Just like force, momentum. Again, we will get some more interesting results in rotational motion as we move on. But here, you can't say that theta is equal to s into r. That is somewhat different. You may suppose s is the linear aspect and theta is the rotational aspect. So s into r is not the theta. That you have derived from the arc by radius. That is somewhat different. But torque and linear momentum you have taken as the moment of force and moment of momentum. This is not that case. Okay. So that is linear motion and its analogical rotational motion. Okay. And in linear motion we are having equations of motion. That is S equal to, or first equation is V is equal to U plus AT, S equal to UT plus half A T square, and V square is equal to U square plus 2AS. What is the rotational analogy here? Omega 0 or omega equal to omega 0 plus alpha t. Corresponding values you have to set the S is theta. Theta is equal to omega 0 t plus half alpha t square. Omega square is equal to omega 0 square plus 2 into alpha into theta. You know from where we have derived all these equations. It's not there in your syllabus now, but we have derived all these equations with the calculus method. So the same method you can opt for deriving the equations of motion also in rotational motion also. It's not necessary to derive again because already we have defined that, but you have to change only the rotations. One I will show you, the first one I will show you. We have taken with the equation A is equal to dV by dt. Here you have to take alpha is equal to d omega by dt. Then alpha dt is equal to d omega. Then integrate alpha into integral dt is equal to integral d omega because alpha is constant. So integral limit is 0 to t. Integral 0 to t means d omega is moving from omega 0 to omega, where omega 0 is the initial angular velocity and omega is the final angular velocity. So alpha into t minus 0 will become omega 0 minus omega. So alpha t is equal to, this will become alpha t is equal to omega 0 minus omega. Omega 0 is equal to omega plus alpha. First equation. Similarly, you can use the same method, but the notations you have to change. Already you have written those equations, so you just refer to the derived equations and you put the corresponding angular moment values there to find out the angular aspect of equations of motion. Okay, so that's for today. We have discussed, or we have started with a rigid body dynamics, and what is we have defined what is a rigid body and two types of rigid body motions, linear motion and rotational motion, and we are focusing more on the rotational aspect of motion. There we have defined torque and angular momentum as moment of force and moment of momentum. Okay, so revise it and we will continue with the next